So we've learned quite a bit about the reactions of alpha-beta unsaturated carbonyl compounds and their reactions with beta-keto esters and beta-diketones. Now we need to learn how to make some of these beta-carbonyl systems. So one way to do this is called the Claisen condensation. So we see our gentleman Claisen came back again. He ended up having a number of named reactions that people use in organic chemistry. We've learned a couple of them in this class. And this is the self-dimerization of simple ester compounds such as ethyl acetate. So we know that esters are less acidic than ketones and aldehydes, but their beta hydrogens are fairly acidic. Frequently when we do these types of condensations with esters, we want to do thermodynamic deprotonations with bases. We want to match the ester component with the corresponding base. So if you end up using ethyl acetate as your reactant, you will want to use sodium ethoxide as the base. That means if you have transesterification during the reaction, it won't do anything. It'll just swap an ethyl for an ethyl. But the reaction pathway we're interested in will be the deprotonation of this hydrogen to make the ester enolate. Once again, this equilibrium will not be very favorable. It'll still favor the neutral ester starting material most of the time, but we'll make small amounts of this reactive ester enolate. Again, ester enolates are more nucleophilic and more basic than ketone or aldehyde enolates. In the similar way that we saw the aldol condensation, we can have esters react with themselves as well. We're going to push the arrows in the same way. Esters will attack the carbonyl carbon in a 1-2 fashion. We don't have any alpha-beta unsaturated options here. And it'll give us this intermediate that is exactly analogous to what we saw in the aldol condensation. Only now we're going to have another option. So whereas in the aldol condensations, we did a proton transfer that took this alpha hydrogen away, now we have the same sort of intermediate we saw in hemiacetal formation. And we know that when we have an oxygen, carbon, oxygen motif, these tetrahedral intermediates can collapse quite readily. So here you see we're going to regenerate our ethoxide base. We'll make this intermediate alpha-beta unsaturated carbonyl compound that very quickly and completely will be converted to the more stabilized enolate. So this enolate forms, and it will not be able to react any further with esters again. This is too weak of a nucleophile to react with ester further. Since this is no longer a strong enough nucleophile, it'll just sit there in the reaction in its anionic form. The equilibrium is essentially irreversible. We would not expect this highly stabilized anion to be taking protons from even ethanol very readily. So this is essentially just going to stop in this form at this moment. Once we add acid to work it up, now we can generate our alpha-beta unsaturated ester, our beta-keto ester product. So this element of making these very stabilized products are important for a lot of the reactions we learn afterwards. This will serve as sort of a ending point to these reactions and will prevent further reactions with other carbonyl groups from taking place. So let's take a look at a modification of the Claisen condensation. But now we're going to have two methyl groups on either side of the ester. And we see here that this reaction does not work. This does not form. And so we need to understand a little bit why this doesn't form. And we're going to go through the same process. We can have deprotonation. This will have no problem occurring. So even though this hydrogen is fairly hindered, alkoxide bases are still fairly small and we can deprotonate it. And now let's look what happens when this tries to react with another ester. So we can imagine the attack on this carbonyl, but now we're going to end up making a fully substituted carbon. And if this were to kick out, we would get the compound shown. But it says that this is not a good reaction. So why is it that this is going to be a very difficult reaction to get away with? So there are two reasons why this is not going to be favorable. One, we are making very hindered, fully substituted carbon centers trying to attack one another. This is going to be a very difficult addition. Because of this steric hindrance. So we end up making a product that is actually going to be quite strained. The second reason this does not work very well is we have no alpha hydrogens. So if you remember on the previous slide, we had potentially equilibrium reactions going back and forth, where this could be going back and forwards. This technically is equilibrium, but this last step here was irreversible. And this was the one that kind of got us stuck in this low energy product state. Since this has no alpha hydrogens to deprotonate, we only have these two methyl groups here. That means that this compound is still reactive. But it's not necessarily reactive in the way you would think. So even if we made small amounts of this, or let's say we made this compound in a different way, and we added sodium ethoxide, it would actually go backwards. So if we have sodium ethoxide around, we know that from our lessons on hemiacetal formation, sodium ethoxide can still attack this carbonyl compound. And if it attacks this carbonyl compound, we actually go backwards to regenerate this highly strained intermediate. And this will actually be able to, again, go backwards again, back to the intermediate components. So this is an example where all of these intermediates are in equilibrium, and because the attack is slow and the reverse process is possible, it never can actually generate the product efficiently. So I think another way of writing this is that might be instructive is we could actually start with this beta keto ester, add in sodium ethoxide, and after workup with acid to get rid of any bases there, we would actually make 2 times this ester product. So these types of processes are called either retroaldol, or in this case it'd be a retro-Claisen reaction, where now this prevents these hindered bonds from forming. And when you see beta keto esters or beta dicarbonyl compounds that have fully substituted carbon centers, you can attack the neighboring ketone and have this group completely break away and break this bond. And this is something to potentially look out for. This is frequently difficult to see at first, but if you see strange bonds being broken, this is something we want to start considering. So now, just like we had crossed aldol condensations, we can also have crossed Claisen condensations. These are going to have very similar features to the Claisen reaction, and that's that one of the reactions does not have any alpha hydrogens. This is going to proceed in exactly the same way. We're going to have sodium ethoxide matched to our ethyl ester and our other ethyl ester. In the event you use something like sodium methoxide as the base, these are usually in excess, and we'd expect actually all the products to end up having methyl esters, or at least most of them having methyl esters due to transesterification, because the methanol solvent would promote this forward in an equilibrium fashion. But getting back to the reaction, we're still going to make this ester enolate. It will attack in a 1-2 fashion on the non-enolizable ester. We will have an intermediate tetrahedral intermediate form that quickly collapses and now makes alpha beta unsaturated esters that under the reaction conditions will be deprotonated and get stuck in this stable conjugate base form until we add our aqueous workup to get the alpha beta unsaturated carbonyl we want out. So if you want to make now beta diester compounds instead of beta keto esters, you can do the exact same thing now using an ester enolate and reacting it with diethyl carbonate. So this will go through the same process as we saw. Again, make a tetrahedral intermediate. It can now lose one of its ethoxides. We make our new beta diester product that will very quickly be deprotonated, because again, these hydrogens are very acidic. And then on workup with aqueous acid, we'll get our beta diester back. Now for the final example of this reaction, we have a similar scenario we're going to walk through that involves different cyclization possibilities now of a beta diester. We're trying to predict the product of the reaction and try to guess why is this preferred. So once again, we have different options for deprotonation. We have a hydrogen next to this ethyl ester here, and we have a hydrogen next to this ethyl ester here. So we can consider drawing either of these ester enolates. Both will be found in this solution. And we can count the number of carbons between the nucleophilic carbon of the enolate. So this would be making a 5-membered ring. The other enolate that we could form on the other side of the molecule that is less substituted. This is going to be 1, 2, 3, 4, 5. So in both cases, we're going to end up having 5-membered rings that will be generated. We can draw these products. I'll go ahead and draw the tetrahedral intermediate. And our beta keto ester product. We can now consider the same reaction here. And they really look quite similar in a lot of ways, right? They're both 5-membered ring beta keto esters. The only thing that really changed was where we had that methyl group. So in one sense, you may be trying to rationalize how this will go. You may say making this intermediate is going to be more difficult, right? Because we have the more substituted center in place, whereas this bond formation should be faster since we do have one hydrogen next to the ester, and that's true. But the big difference here between these two compounds is the product of this molecule. We have this methyl that is found between the two carbonyls, whereas here we have a hydrogen between these two carbonyls. So since we're under conditions with sodium ethoxide, this hydrogen will be directly deprotonated immediately in solution to give us this new enolate that gets stuck and can't react any further. Whereas this methyl keeps this in place, which means sodium ethoxide will actually be able to come back and attack to ring open. So this is in the same rationale as to why we weren't able to do an intermolecular condensation of two esters when we have a fully substituted carbon next door. Now we're seeing this will discourage this pathway from being productive. That's because each of these ester enolates are in equilibrium with one another. So even if some of these molecules decide to go down this path and make some of this for a little while, the ethoxide will actually be able to react again with this product and take it back and go through this alternative sequence that will lead to this final product that can't go any further. So it's this step that is irreversible that makes this product be favored initially, and then, of course, after aqueous workup, we would isolate this beta keto ester.